Hi, everyone. Thank you all for joining us in the process of identifying the most important tuning parameters of random forest. This is Team Optimal Design. First, let me introduce you to random forest. Random forest is one of the most successful algorithms for tackling classification problems, and there are 7 important tuning parameters involved. One way to measure the response or the performance of random forest is through cross-validation accuracy, which ranges from 0 to 1, with it, the higher, the better. The goal of the problem is to find the most important tuning parameters of random forest. And to do it, we will want to also focus on inference over prediction. And we're interested in the estimations of all effects. The codings are as shown below, and for our requirements due to budgets, our maximum number of tests is 35. We also assume our designs to be completely randomized, and our auxiliary data set is the diabetes health indicator one. For our research process, we will first select our experimental designs and then move down into our data analysis process. First, onto our experimental design. Our first design is the fractional factorial design, which we have calculated maximum runs to be 35 and minimum run to be 29 runs. And so as a result, we propose a resolution for fractional factorial design with 32 runs so that we can also leave 3 for confirmation experiments. The design is shown in the middle, and for evaluation, as shown on color map and VIF, there are no significant multicollinearity for main effects only. Our second choice is the optimal design. We propose an optimal design with 32 runs as it is a multiple of 4, and we will also be able to leave 3 for confirmation experiments. Our design is criterion D, and the design is as shown in the middle. For evaluation, as shown in color map and VIF, there are no significant multicollinearity for all effects.
Now, we compare the 2 designs through practical terms and statistical terms. Regarding practical terms, both designs have the same number of runs, but the optimal design is better because it can estimate 21 two-factor interaction effects, while fractional factorial design can only estimate 15. Regarding statistical terms, although fractional factorial design is orthogonal, the optimal design is better because it has no fully aliasing and less significant multicollinearity according to the color map. Remarkably, the optimal design's VIF includes intercept, main effects, treatment factors, and their two-factor interactions with all VIF smaller than 5, showing that it has no multicollinearity. In contrast, fractional factorial design has a very multicollinearity between two-factor interactions, and its VIF cannot estimate all 21 interactions. Thus, we recommend the optimal design. Furthermore, we compare our optimal design with a design generated by a commercial software. Although the commercial software design has fewer number of runs that indicate less expensive experiments, our optimal design is still better because it is able to estimate all of the effects and has less significant multicollinearity. Moving on to the data analysis part. We first collect data using our recommended optimal design by using the diabetes auxiliary dataset and get response Y, which is cross-validation accuracy for each run. We then fit the data to our initial model, which includes all main effects and 2 interaction effects, and get the result of 13 significant effects using a significance level of 5%. According to the effect hierarchy principle, we keep the insignificant main effects A, B, C, D in the next model because they are involved in significant two-factor interactions. Then we use the aforementioned 13 significant effects plus 4 insignificant main effects in the model 2 and repeat the same thinking process to get a result of 10 significant effects. Similarly, we get 7 significant effects in model 3. Now, B and D are not involved in any significant two-factor interaction, so we eliminate them.
For our final model, we have 3 significant main effects, class WT, cutoff, max nodes, and 4 significant two-factor interactions as shown in the slide. We also keep the insignificant main effects in tree and replace in the model because the effect hierarchy principle indicates that if a model contains a high-order term, it should also contain all the lower-order terms that compose it. Below, we show the formula of our model. Next, we'll look at the residual analysis. And according to the 3 plots, the normality, constant variance, and independent assumptions are all satisfied. The model also has an R-square of 0.924, indicating that our model is a good fit with data. And then we first identify the optimal setting that gives us the maximum yield of the response and uses this setting to perform 3 confirmation runs. The result shows that our predicted value is less than 3% off from the observed response, which further verifies our model. So in conclusion, the significant tuning parameters we have identified in this model are class WT, cutoff, and max nodes. The respective setting of 0.5, 0.2, and 10 will yield the optimal response. We also identified 4 significant two-factor interactions as listed. So we recommend to set the tuning parameters at the above levels if someone is using the random forest algorithm. Also, since the interaction between entry and replace is significant, one should also look out for these parameters during setting. Finally, regarding the strengths of our optimal design, our design is able to estimate all main effects and two-factor interactions, and our model doesn't have fully aliasing relationship, and it has less severe multicollinearity. In terms of our final model, our model satisfies all the assumptions and is a good fit to the data. Thank you for watching.